All right. Good morning and welcome to session number 399 of Chai and Wine. And today I have great pleasure in introducing today's speaker, Dr. Srimati Srinivasan. So she is a bachelor's in electronics engineering, but eventually chose mathematics as she found mathematics more interesting. So currently she is a faculty member at TIFR in the School of Math, and today she is going to talk about proofs and paradoxes in mathematics.
Thank you. Okay.
Start the screen share.
The screen is shared already.
No, Zoom, on Zoom.
Oh, okay. Fine.
Yeah, good.
This fine.
That
So I have to
move it so far.
sorry. Okay. Okay. So thanks for the invitation to speak here. So I want to talk about some proofs and paradoxes in mathematics in the mathematical context. So the first part of the talk, I want to talk about proofs and some common methods of proof that we use in proving some statements. And in second half of the talk, I want to talk about paradoxes in mathematics, and I want to uh, say how they are related. Okay, so let me start with proof. So what is a proof? So the Oxford Language Dictionary defines proof to be an evidence or an argument establishing a fact or truth of a statement. Okay, so you're given a statement and we want to find out whether it is true or false. And if you think it is true, you must be able to provide a proof for that statement. Okay, so that is called proof. And the kinds of proofs that will be interested in this talk will be of mathematical nature. So what I mean by mathematical nature is that so I want to prove some statement based on rigorous logical reasoning. Okay, so for example, let's consider the statement that product of two odd numbers is odd. Okay, so everybody I hope will agree with this fact that product of two odd numbers is odd. And consider this following argument that 3 times 1 is 3, which is odd. 3 and 1 are odd, and 3 is also odd. 3 times 1 is odd. 5 times 9 is odd again. 19 times 21 is odd. 1001 times 2999 is odd. And then you conclude like it looks like for all these numbers, product of odd is odd. So I conclude that product of odd is odd. Yes. Huh. No, numbers. When I say numbers, I mean natural numbers, so not decimals. I'm just think of all the numbers bigger than 0, which are whole numbers. Like. Okay. Okay. So so the statement is this. The statement is that the product of two odd numbers is odd. Odd, I mean, like I'm looking at natural numbers. Odd numbers are not the ones that are they're not the ones which are divisible by 2. So if I take two odd numbers, it has to be odd. So there is a everybody agrees with this fact. And if I want to prove the statement, the argument, suppose I give you this argument, like 3 times 1 is 3 and 5 times 9 is 45. All these numbers, for all these numbers, it looks like product of odd numbers is odd. So therefore, I conclude that, as I go, beyond 1000, as I keep increasing my size of the number, the product is also going to be odd. So I just say that, from the above examples, we conclude that the product of odd numbers is odd. Well, does this constitute a proof? Right? Because I have checked only finitely many of them. There are infinitely many numbers. I haven't checked all of them. And this doesn't constitute a valid mathematical proof. So this is not considered as a proof in mathematics. Right? You just take some cases and then show that the argument goes through. So therefore, it goes through for everything. It's not a valid proof in mathematics. Okay, so in general mathematics, what we do is we discover new theorems and proofs from axioms and you formulate new conjectures. So these are some terminologies that we use in mathematics, and let me just go over each of them. So axioms, what are axioms? It's the statements which are like building blocks. You take them to be true to start with. These are like the rules, and you play the game from there. Okay, so for example, if I say if A equals to B and B equal to C, then A equal to C. Okay, so that is something that everybody should be agreeing with. Okay, we start from there. And a theorem is something, a statement which will have a formal proof. It is a statement which is not very obvious, but one must be able to prove it through mathematical reasoning. The one that I just mentioned before is not a proof. A proof is a set of logical arguments which establishes validity of a statement. Okay, so via logical reasoning, go from one step to other. You want to explain why it is true logically, and then deduce the conclusion based on each of the steps. And conjectures are statements that are believed to be true, but usually based on evidences, but we don't know, we don't have the proof yet, but we think that that has to be true somehow. We just don't have proof yet. Okay, so these are some of the terminologies that we use, that we encounter when we're doing mathematics. So the main focus of this talk would be on proof techniques. So first half would be, I'll be talking about proof techniques. Suppose if I give you a statement, I want to provide a proof of the statement. And if I want to provide a proof, what are the methods that we can use to provide a proof? Okay, some commonly used methods. These are not the exhaustive ones, but some commonly used methods in mathematics to provide proofs. Okay, so here are some example that we just saw. The product of two odd numbers is odd. Okay, so the argument that I gave before is not a proof because it is not exhaustive. So I want to give an actual proof. So here is a direct proof. A direct proof means the sequence of arguments deduced from previously known statements, and that gives you the conclusion of the statement. Okay, that proves the validity of the statement. Okay, so here is the one. So odd number means it's not divisible by 2. So it must be of this form, 2n plus 1. I think this is not working. Yeah. So odd number basically means you have A and B odd numbers means it is not divisible by 2. So it must be of the form 2 times n plus 1 and 2 times m plus 1. Okay, so n and m are some numbers. So this A is an odd number, B is an odd number, and you want to show that the product is odd again. The battery will not, okay. Okay, so this is the proof. The actual proof is like you take A times B, then A times B will be of this form, 2n plus 1 times 2m plus 1. And if you just expand the brackets, when you expand the brackets, what you have is you get 4nm plus 2n plus 2m plus 1. And then you can take the 2 outside the brackets, and then you get something. So you get 2 times something plus 1. So 2 times something plus 1 is again odd, right? So this thing here is odd because it is of the form 2 times some number plus 1. So you started with 2 odd numbers, so they are all going to be of this form for some m and n. And then I take the product and multiply them together, and the resulting thing is also of this form 2 times some number plus 1. So what this says is that you take 2 odd numbers, and the product is going to be odd. Okay, so now would you agree that this is a formal proof? This is like a mathematical proof which will just exhaust all the cases, right? Independent of what your A and B are, independent of what your numbers are, I give a proof, I give like a 4-line proof which will tell you that for any A and B, the product, if A and B are odd, the product is odd. Okay, so this is exhaustive. Okay. Now I just want to talk about some commonly used proof techniques in mathematics. So these are some of the techniques that we use, and I want to just go over each of these very briefly. So direct proof, constructive, non-constructive, visual, proof by cases, proof by induction and contradiction. Okay, so let's just let me just briefly explain how things are proven in mathematics. So let's say constructive proof. So the constructive proof is usually about proving a statement about some existence. So let's say you want to show that there is some x, we don't know what that x is, such that some statement P of X is true. P of X is a statement, and we want to find we want to show that there exists some X for which the statement is true. Okay, the constructive proof works by explicitly producing an example of such an X. So I tell that the statement is true for some X, and the proof is find such an X. Give me such an X for which this is true, and the statement will be valid. Okay, so here is an example. Let's say you want to prove that there exist natural numbers x, y, and z such that x square plus y square equals z square. Okay, so the question, the statement is about existence of something. So you want to prove some triplets x, y, and z satisfy this equation. These are called Pythagorean triples. And how will you prove this theorem? Explicit, yeah. So you take 3, 4, and 5. I produce explicitly an example of x, y, and z such that 3 square plus 4 square is 5 square. Okay, so this proves the theorem. Okay, so there's nothing more to do. You give me an explicit example. You construct an example for which the statement is true. Okay, so non-constructive proofs work the other way. So suppose you want to show the same statement. Let's say the statement is the same. P of X is the same. And you want to show that there exists some X for which the statement is true. Now, it may not be easy to produce such an X explicitly. Like in the previous example, you have specific example of X, Y, and Z for which the statement holds. In many cases, you will not be able to produce such an example of an element or some triplets satisfying that. Then in this case, what we do is we just find some other method to prove the existence without explicitly producing the element. Okay, so here is the theorem. There are at least 2 people in this room born on the same month. Do you agree with this statement? Yes. Why is that? Yes, so there are only 12 months in a year, and there are at least 13 people in this room. So at least 2 of them should be sharing the same birth month. Right, so this is a very simple logical argument to tell that, you know, some pair of them will be sharing same birthdays. It's not birthdays, some birth month. And similarly, if you have in the, let's say in the world, in the entire world, there are at least 2 people sharing the same birthdays, right? Because there are more than 365 people in the world, so 2 of them must be sharing the same birthday. So it's a perfectly valid logical reasoning, which will prove the statement. Okay, this principle is called pigeonhole principle. It comes from the scenario that if you have, let's say 12 slots, and if you have 13 pigeons, you want to put 1 in each. 2 of them will be sharing 1 slot. Okay, so this is called pigeonhole principle. Okay, so the second proof technique is visual proof. It is just like you are given a statement which is not really visual, but then you want to visualize the statement in terms of geometric objects and deduce it using known results. Okay, here's the theorem that sum of 2 sides of a triangle is larger than the third side. Okay, so I hope many of you must have seen the statement when you were in high school. Sum of 2 sides of a triangle is larger than the third side. There are many proofs of the statement, and you can prove it in many different ways. But I want to give anybody knows a favorite proof of how to show this? There is a triangle, 2 sides, and one more time. Sorry. Okay, so yeah, you're trying to visualize that, but here is a simple visual proof. Otherwise, the triangle will not be formed as a statement. So the visual proof is like this: you have 2 triangles. Sorry, you have 2 sides. You have 3 sides A, B, and C. Let's say A is the longest side. Okay, so the hope is that the longest side will be, let's say, if it is larger than the sum of other 2 sides. You take a circle with radius A, B, and C, which are the shorter sides, and then you make a circle with B and C as a radius. Then you can see that if A is going to be bigger than sum of B and C, the triangles don't really touch each other. You cannot form a triangle if B and C are, the sum of B and C is shorter, right? Because the sum of B and C will be, if you look at the circle, the distance from one point to the other point, in one center to the other center, is actually a, but then the radius, sum of the radius will be less than this line segment. So it's not going to form a triangle if it is not the case. Okay, so the sum of two sides is going to be larger than the third side. Okay, so this is just a straight visual proof that things don't work otherwise. Okay, and proof by cases is the following. So what the way it works is that you are given a statement, you're given a problem, you want to split it into many smaller parts, and you solve each part separately and exhaust all the possibilities. Okay, so here is a theorem, like for every integer n square is bigger than n. Okay, every integer n square is bigger than n. I want to show, so I hope everybody agrees with this, right? N square is going to be bigger than n for every integer. There are three possible cases. I'm splitting into cases: n equal to 0, n is bigger than 0, n is less than 0. Okay. Now what happens when n is equal to 0? When n is equal to 0, 0 square equal to 0. So this is true. And when n is bigger than 0, then that means that you're looking at only integers. So n is bigger than or equal to 1. So you multiply both the sides by n. So n is bigger than or equal to 1. I multiply by n on this side. I multiply by n on the other side. Then you get n squared is bigger than or equal to n. Right? This is true. This holds. And when n is less than 0, that means n is negative. N square is going to be positive, and positive numbers are always bigger than negative numbers. 1 comes here. 1 square is equal to 1. So it's bigger than or equal to. So the statement is true for all these cases. Right? So I just split this given situation into 3 different cases: n equal to 0, bigger than 0, less than 0. And for each case, I prove this statement, which will exhaust all the possibilities. Okay? So this is another proof. This is a valid proof of this statement. Okay, so the next proof would be proof by contradiction. So in this case, what you do is to show that a statement is true, you assume that it is false, and show that if you assume it to be otherwise, then there is a contradiction in the argument. Okay, there's a contradiction, there's some absurdity comes here. So here is an example of proof by contradiction. So there are infinitely many prime numbers. Okay, so everybody is familiar with prime numbers. Okay, prime number is a number which is not divisible by any other number other than 1 and itself. Okay, so there is no other divisors other than, for example, 3 is prime, 2 is prime, 5 is prime, 7 is prime, 11, 17, for example, is prime. Okay, so the theorem states that there are infinitely many of them. Okay, you can find as many prime numbers as possible. Okay, so here is an argument. Anybody is familiar with the proof of this? Yeah. Yes, this is for 3. Yes, the same argument goes for any n. Right. So assume not. Suppose there are not infinitely many primes. Let's say there are only finite set of prime numbers. Let's call this P1, P2 up till Pn. These are the only prime numbers. Suppose there is the case where n can be anything, any finite number. N can be 100, 1000, can be anything. But suppose there are only finitely many of them. Then what you do is you take this number, the product of all these prime numbers plus 1. Right? Now this number Q is larger than every prime number in the set. Right? Q is bigger than Pi for every I. So therefore it cannot be prime, right? Because if it were prime, it will be in one of these, it will be in the set. But it is clearly bigger than each of these. So therefore it cannot be in this set. So it is not a prime number. So some prime number divides Q. If it is not a prime number and some other prime number divides, right? For example, 6 is not a prime number because 3 divides it, 2 divides it. Okay, so since q is not a prime number, some other prime divides it, but these are the only set of primes that we have. We have no more. So let's say pi divides q, for example. But pi also divides the product, p1, p2 up to pn. So if a number divides this product, and if the number divides q also, then the number also should divide the difference, right? Right, so you agree with this? So 3 divides 6, 3 divides 9, so it divides the difference. Okay, so pi should divide the difference. But what is the difference? 1. So no prime number can divide 1, right? So therefore, this is a contradiction. If you assume that there are only finitely many primes, you arrive at a contradiction. Okay, so therefore, there are infinitely many primes. Okay, so this is called proof by contradiction. So you assume that the statement is not true, and then you arrive at some contradiction. Okay, so therefore, the original statement has to be true. Okay, there has to be infinitely many primes, right? Okay, so the other commonly used proof technique is principle of induction. This is due to Pascal, who formally stated this. So the way the proof goes is the following. So suppose you have a statement P of n. Okay, P of n is a statement involving a natural number n. Okay, so n is a natural number and P of n is some statement involving the natural number. You want to show that P of n is true. Okay, so you want to prove it. And how do I prove the statement? We take the following steps. The first step is you want to show that the base case is true. When I say I want to show that P of n is true, I want to show that the statement is true for every n, every natural number the statement holds. So what I do is I take the base case, so P of 0 or P of 1, depending on where you want to start with. Let's say I assume that, let's say that I show that P of 1 is true. Then what I do is I show that if P of I is true for some I, then P of I plus 1 is also true. Okay, then this essentially tells you that P of n is true for all n, right? So let's say you want to show that P of 5 is true. And how will the proof go? P of 1 is true, that I already proved. And if P of 1 is true, by this statement, P of 2 is true. And again by this statement, if P of 2 is true, P of 3 is true. If P of 3 is true, P of 4 is true. P of 4 is true, P of 5 is true. Okay, so therefore I show P of 5 is true. The same technique can be used when n is any large number. Okay? So you can show that P of n is true for every n if we can prove these two statements. Okay, so I hope this makes logical sense, right? To show that P of n is true for P of 100, you just start with P of 1 and then say that P of 2 is true, P of 3 is true, because you have proven this statement. Starting from this statement, you prove this statement, and then once you prove this statement, it is true for all n. Okay, so this is called principle of mathematical induction. I want to give an example. Let's say we have this theorem that P of n is the statement that the sum of n natural numbers from 1 to n is n times n plus 1 over 2. Okay, so this also is a formula you've seen in high school, right? The sum of first n numbers is n times n plus 1 is n over 2. Okay, this is true for every n, independent of what n is. N can be 500, 1,000, a million, doesn't matter. So this is true. And how do I prove this statement? So using induction, the base case is P of 1. Okay, P of 1 is true because 1 is 1 times 1 plus 1 over 2. Right? When you just take n equals 1, 1 equals 1. So this holds. The base case holds. And let's say suppose P of k is true. I want to show that P of k plus 1 is also true. So let's say P of k is true. That means I'm saying that the sum of first k entries, 1 to k, is k times k plus 1 over 2. So that is known. I want to check if we take first k plus 1 numbers, you get the same formula. Well, you just take this k plus 1 numbers, then first k numbers, we already know it is true. So the first k numbers will give you k times k plus 1 over 2 because you assume it is true. Now you add k plus 1 here, and then it's just arithmetic. You just take 2 here, multiply by 2, and then take k plus 1 as a common factor. Then you have k plus 1 times k plus 2, but k plus 2 is k plus 1 plus 1 divided by 2. Right? So what we have is sum of k plus 1 numbers is k plus 1 times k plus 1 over 2. Right? Right? If p of k is true, that means if sum of k numbers, first k numbers is just k times k plus 1 or 2, I have shown that the sum of first k plus 1 numbers is this. Okay, so from here, by principle of mathematical induction, you have shown that p of k plus 1 is true if p of k is true. So therefore, p of n is true for all n. So if I want to show that p of, let's say 50 is true, then what do? Sum of first 50 numbers, I want to show that is 50 times 51 divided by 2. That is true because I know that p of 1 is true. When p of 1 is true, I know that p of 2 is true by this argument. But the same argument, if p of 2 is true, I know p of 3 is true, and so on. So I know p of 49 is true, so therefore p of 50 is true.
Given that p of n is true, assuming that p of n is true, we are trying to prove that p of n plus 1 is
correct, right? So that is the but you have to start with the base case. So you have to show that p of 1 is true, and then from there you show that if p of k is true, p of k plus 1 is true. Okay, so if you don't have the base case, then it doesn't go through. Right? It depends on what the problem is about. If I say it is true for all natural numbers bigger than 0, depends on what it is. If I say that if this is true, let's say for all integers bigger than or equal to 1, then the base case would be 1. If I say it is true for all numbers bigger than or equal to 0, the base case would be 0. Right? Because 0 plus 1 plus 1, so you start from that number, start from that 0 number. Yes, depends on what the statement tells you. So if the statement tells the sum of first n numbers starting from 1, then you cannot start from 0 anyway. If you start from 0, if you say 0 plus 1 plus something, you start from 0, it works. Not necessarily. Let's suppose, no, suppose it is true for 0 also, but then the thing is, you start with the base case from which you can take the next step. What you want to show. Suppose if my theorem is that p of n is true for n bigger than or equal to 1, then you don't want to go to 0, n equal to 0. You start with n equal to 1. Right? And right, you want to show if it is for all bigger than or equal to 1, then you want to start with 1. Right? So I think that is okay. So this is called principle of mathematical induction, and it is used in many scenarios where you have to prove a statement for arbitrary n, and you don't want to go case by case. You don't want to exhaust all the possibilities one by one, but instead you want to provide an argument that this will work if the base case works, and if I show that iteratively this works, then all the cases will work. Yeah, so because n is the natural number in this case, so you want to go one step at a time. Sorry? I don't hear. What is that? Sum of minus 1?
Can you speak a bit louder?
Oh, that one is yeah, but I don't know if we can. I don't know. Some of that's not that is some of natural numbers leading to. I don't think it is true.
All natural numbers up to infinity is minus 100.
No, I don't think it is true in normal arithmetic. It is not true at all.
Okay, we'll come to it.
Not true. Not true. Okay. Okay, so by principle of induction, this is true for all n. Okay, so these are some of the methods of proofs. Now I want to talk about paradoxes. Okay, so sorry.
Apart from this, the method of proof in its first time.
I think these are the ones I listed.
So the question is, are these the exhaustive proofs?
No, these
or
are not
are
exhaustive at all. No. These are just some commonly employed proofs in mathematics. There are also other proofs. You can use probabilistic
sufficient
proofs.
to pass bachelor's?
I don't know. I don't know what bachelor course requires. But I don't know. Okay. So this is some commonly used proof techniques. Okay. So now, do you know what is a proof? You know some methods of proofs. You know how to show a statement, based on one of these proof techniques. Now I want to talk about the other side of the story. The other side of the story is paradox. Okay, so what are paradoxes and why do we talk about this and how are they related to proofs? Okay, so the word paradox comes from para and doxa in Greek. Para means contrary to and doxa is opinion. Okay, so put together, this means contrary to one's opinion. So what it means is that it is a statement which appears contrary to one's expectations or understanding or opinion. Okay, so if I give you a statement, it looks like, yes.
Out of the several proofs you showed, how does one select the particular?
It depends on the problem. I think you should just one method may not work for other. You just have an intuition of which one will work, right? For example, for that formula that I gave, let's say I have this formula, and let's say if I want you to prove this by visual proof, there's no way to, I don't know if there is any. This seems like a plausible way to go because it naturally leads to going from one integer to other integer. For incrementing by one seems like a thing to do whenever you have natural numbers statement involving natural numbers. But if you ask me to prove in any other method, I don't know if there is a way. If you ask me to prove visually, I don't know how to visualize this, for example. And if I ask you to prove the sum of two sides of a triangle is larger than third side by induction, I don't think there is any proof like that. So it depends on the problem, purely on the problem, what it is asking you to prove.
Also, another online question: is proving by any one method sufficient, or like scientists say, there should be a confirmation from this experiment?
No. One solid proof is good enough to establish the truth of the statement, but the proof that I write down may not be as pleasing and as beautiful as someone else's proof. So there can be multiple proofs for the same statement.
But that's not a requirement.
That a requirement for what? For establishing the truth. For establishing the truth, any proof will do. Yes. But then, if you're looking at some proof may not be as pleasing, as beautiful as the other one, so you just pick the one that is.
I guess person that.
Okay. All right. Okay, so the second side of the other side of the story is paradoxes. So paradox means, as I said, is a statement which is contrary to one's expectations or understanding. So it is a statement which might look like, which looks like it is, there's something weird about the statement. Okay, the first, it may go either way. The first time you look at the statement, it looks like something should be wrong about the statement, and you go closely examine to find whether it is true or false. And the other way also, it looks like the statement is absolutely fine, it's absolutely true, but if you closely look at it, it leads to some contradictions. Okay, so it goes against human intuition or expectation. Okay, so those are called paradoxes. So it's a statement claiming something which goes beyond common opinion or even against the common opinion. Okay, and it usually leads to self-contradictory or logically unacceptable situation. Okay, so this is all the definition comes from these sources: Wikipedia and Stanford Encyclopedia of Philosophy. Okay, so I'll just give you a very fundamental example. So this is called the Socrates paradox. So Socrates, as you must have heard, he's a philosopher way back in BC. So he said this, Plato's account says that he mentioned the statement that I know nothing. Okay, so if you just look at the statement, I know that I know nothing, there's something weird about the statement. There's something strange.
Then how you know?
Yeah, if you know nothing, then how do you know? If you really know nothing, then you should not be knowing that you know nothing, right? So if you know that you know nothing, that means you know nothing is not a right statement. You know something. Okay, so this is called Socrates paradox. Okay, so this statement, the first time you look, it may be okay, I know nothing. But then if you look at it more carefully, there is something going on there. You cannot absolutely know nothing if you know that you know nothing. Okay. So he also mentioned that this actually there is some story behind it, that he realized that many people talk about things that they don't know about, and then he realized that I basically know nothing. So he said, like, I know that I know nothing, so actually I'm a little wiser than other people, is what his statement was. Okay. Okay. So paradoxes, they were analyzed by these this 20th century philosopher Quine. He was one of the most influential philosopher and a logician in the 20th century. And he actually classified paradoxes into three categories: veridical paradox, falsidical paradox, and antinomy. Okay, so veridical paradox, what it means is that it is actually a true statement, but it appears false for some reason. The first time you look at it, it looks like, no, it is false, it is absurd. But if you look at it, it's actually true. A falsidical paradox is the other way around. It looks false, but it is actually a false, but someone gave a proof or kind of a fallacious proof that it is true. There is some fallacy in the argument of the proof, which says like this has to be true, but it looks false. Antinomy is like something which is self-contradictory. It's a statement which contradicts itself. Yes. I'll come to that. Yes, right. So this is actually comes from his paper on ways of paradox and other essays. Okay, so I'll just briefly talk about paradoxes in this context. So first one is I want to talk about interesting numbers. So this story goes back to Hardy and Ramanujan. They were two great mathematicians, but they were just they were discussing about interesting and uninteresting numbers. So they're talking about which numbers are interesting, which numbers are not interesting. And Hardy told Ramanujan that his taxi number 1729 seems uninteresting. Okay, and then I think many of you would have heard of the story that Ramanujan contradicted that it is interesting because it is the smallest number, which is the sum of two cubes in two different ways. So 1729 can be written as sum of two cubes in two different ways. It is the smallest such number. Okay. So this is so therefore he concluded. He said like 1729 is not uninteresting. 1729 is an interesting number because it is the smallest number which can be written as sum of two cubes in two different ways. Yes, so that is again the question. So we don't know what is their definition. It goes with common opinion. So you would agree that 1729 is interesting, right? Because it is the smallest number which can be written as sum of two cubes. It is interesting.
But why did they say that all numbers above above x are interesting? And then
there must be something unique about that number.
Then x also is interesting because what is the large uninteresting number?
Yes. That is actually the thing. That the thing is, if I say that 1729 is interesting, then you would agree because I have written 1729 two different ways, and it is the smallest such number. But if I give you some other random number, 685, we don't know if it is interesting or not, right? But you definitely agree this is interesting number. Now, the paradox is this. So the statement is that every natural number is interesting. So if you first look at it, then you think it is not probably true. How can 685 be interesting? 1005 is interesting. I don't know. How is every natural number interesting? So it actually came from the Ramanujan and Hardy story. The statement seems false, but it's actually true. Every number is interesting. And I'm going to prove it by contradiction. Here's the proof by contradiction. Suppose if S is a set of all uninteresting numbers. Okay, so every natural number, I'm taking all the numbers bigger than or equal to 0. So I'm just taking the set of all uninteresting numbers, putting them together in a set. Okay. Now, suppose if S is not empty, that means there is some number in that. There is a smallest number in that. The smallest number itself is interesting because it is the smallest uninteresting number. So therefore, it is interesting. If it is interesting, it cannot be in S because S contains only uninteresting numbers. So S has to be empty. So every number is interesting. Every number is boring. Again, define boring. What is boring? So I believe that 1729 is not boring. I think my definition is that it's not boring because I mean it depends on what do you call as interesting. So it comes from most of the human language. When you say interesting, there must be something peculiar about that number. Some characteristic of this number which is unique to that number. Right? And in this case, you cannot have such number because if there is some number that there is something smallest of that type, and if it is smallest of the type, it is unique to that number. It is interesting. So it cannot be in the set. Right? So it is called the interesting number paradox. So at first look, it looks like it is an absurd statement. Not every number can be interesting, but it is true. Every number is interesting. Okay, so it's a contradiction. So it's proof by contradiction. I have proven a paradox, paradoxical statement using, I give a mathematical proof to a paradoxical statement here. Okay. Okay, the second paradox is this: all horses are of same color. So this is called the horse paradox. Okay, so anybody who agrees with this, it is false, right? Of course, it is false. I have seen horses of black and white color. So not all horses will be of same color, for sure. Huh?
You have a visual proof of that.
I have a proof for that. I'm going to prove that all horses are of the same color. Okay, the proof is by induction. Okay, so let's say base case is true. If there is one horse, it is of the same color. There is no more horses. It is fine. Now, suppose like any n set of n horses are of the same color. I take any n horse, n can be anything, and I suppose that all of them are of the same color. Okay. Then I want to show that if I want to use induction, I want to show that any n plus 1 horses will be of the same color. Okay, then I want to show this, but here is the visual proof. Okay, so you have n plus 1 horses. You have first n horses in the red box, which is of the same color. The second n boxes, this is starting from 2 to n plus 1. There are still n of them. They are of the same color. But now this is of the same color as this, of the same color as this. So all of them are of the same color. So this is so if n of them are of the same color, n plus 1 is of the same color. So by principle of induction, any set of horses will be of the same color. Huh?
By asking colorblind person to tell this color.
Colorblind person.
No,
Not this.
But what if you not change between your
Yes.
like suppose I present a proof by one of the proof methods that a certain statement is true. How would you like challenge it upon that? In this case, because it is logically, everyone knows that you can challenge. Okay, even if you use the correct proof method, this statement is false. But in a lot of mathematical problems, you
So
are not able to detect that error.
that is not possible. So if it is a correct, this is definitely a false statement. Everybody knows it's a false statement. I have demonstrated a proof. The only way in this case it is that there is something wrong with the proof. I've used induction, but I've not used it in the right way. So I want to demonstrate that there is a false, there's something going on here which is wrong. I'm not using the proof in the right way. It is not the correct proof. That is why the statement is wrong. So there can be proofs which look like it is correct. It works through if you just apply the principle, but then there is something subtle going on here which you are not able to notice.
statement that first and horses
Yeah.
are true. You're probably not allowed to use the box from
2 to n plus 1 is still n horses. The assumption, the hypothesis is any set of n horses are of the same color, any set of n horses. Then I want to show that any set of n plus 1 horses will be of same color, and this is the proof. Yes.
Has to be read like all the others because you have taken that one as a base case, but then the second one you have taken two as a base case, and this is illogical because you can't see base case.
I'm not changing the base case. I'm just taking the n is to be 1. N is 1 base case. Principle of induction says that you establish a base case. You suppose if you take base case is true, for k it is true, and if you show that k plus 1 is true, then it's true for every n. So which particular case is going wrong here? Right. The thing is here you will need at least 3 horses because otherwise there will be nothing in the center to compare to. If there are only 2 horses, the center box will not be there. Right? For n equals 2, it fails because the argument fails here. The second step of the argument, which says that if it is true for n, it is true for n plus 1, fails here because when you take n equals 2, then you will have only 2 horses. The first horse is one color, second horse can be of different color. So there is nothing in between. For n plus 1, I'm just putting a box here because it looks like there is something in between to compare with this to this and this to this. But if n is equal to 2, there is nothing in between. There is no intersection. There's a set of 2 horses. First one can be white, second one can be black, and there is absolutely nothing in between. But if there is at least 3 horses, then you will have 1, 2, and 3. The first 2 will be of same color, second 2 will be of same color, then all of them will be of same color. But for n equals 2, it fails because the second step of the argument fails. So there is the problem. Okay, so the induction principle is completely fine. It is just the way it is used in this proof is incorrect. Okay, so this argument that if this first set of n is of same color, second set of n is same color, then the entire set will be of same color is a wrong argument because you may not have anything in between to compare to. Okay, so it works only for at least 3 horses. For 2 horses, it's not true. Okay, so there is this comes under the second category, falsidical paradox, because the statement is absurd. It is false. We know that it's false. It's actually false. It appears false. It's actually false. But then there is something wrong with the demonstration. Something wrong with the proof. Okay, so this is also considered as paradox. Now, sorry. Crow. Okay. All the crows are black. Like it still have. We know that it is true, but then this proof doesn't apply there anyway. Because this proof doesn't apply there. It is. We know it is true, but then this proof doesn't apply there in this case. Yeah. If it is 3 crows are black, if you agree with that base case that 3 crows are black, then we can establish that. The same with horses. If you agree that any 3 horses are same color, then you can, but it's not true. So this is a wrong proof. Yes. It can be any color. Color is not specified. Let's say white. It doesn't matter which color. Same color means they're all of the same particular color. Any of them, like white, let's say white. All of them are white color. So, yeah, so the problem is that the proof is wrong. Okay, the principle of induction is correct, but the way it is used is wrong. Okay, so the next paradox I want to talk about is the barber paradox. I think this is also a very famous paradox. So let's say you have a barber in a town who shaves only those who do not shave themselves. Okay, this seems like a perfectly valid statement. You have a story starting, with the statement that there is a barber who shaves all those who do not shave themselves. Okay, fine. Okay, now this seems like perfectly fine statement. But now if you ask this question, who shaves the barber? Okay, so first there are only two possibilities. Either he shaves himself or she doesn't. Suppose if the barber shaves himself, the problem is he shaves only those who do not shave themselves. So he cannot shave himself. Right? So if he shaves himself, he cannot shave himself. But if he does not shave himself, he has to shave all those who do not shave themselves. So he has to shave himself. But there is only one barber in the town. There is only one barber who shaves all those and only those who do not shave themselves. Yes, yes. Yes.
Statement says only but not all. Second is still allowed.
This is still around. No, this is only those, all those, the barber in town shaves all those and only those, all those and only those. It doesn't matter. I mean, well, the question is like, he might, I don't want to go into this, but the question is, he's a male, let's say, who shaves him? Okay, so this is called the barber paradox. Okay, so the statement which looks fine, just when you look at it first time, might not actually make any sense if you look at it carefully. Okay, so the statement doesn't make any sense. It's a paradox. Okay, so such a barber does not exist, so the barber shop is empty. Okay. Okay, so the next paradox is called Russell paradox. It is actually derived from the barber paradox. Okay, so it's actually a mathematical formulation which is based on barber paradox. So mathematical formulation involves the definition of sets. Okay, I hope everybody would have seen the definition of a set. A set is just a collection of things or objects. Okay, so you collect some things together, put them together, form a collection. That collection is called a set. It can be any collection. Okay, the elements of the set, the things in the set are called elements. Okay, so let's say I have an example, empty set, a set with nothing. It's a set. Okay, let's take a set F, which has apples, oranges, and bananas. It is a set. Okay, it has three things in it. It has three elements. Apple is an element, orange is an element, banana is an element. And you form another set which has all the natural numbers in it. There's a set. And let's say you have a set which contains two different sets. Okay, so you have 2, 3, 4 is a set. 87 and 64 is another set. You take two different sets, put them together, you form a new set. Yes.
The paradox is a set that contains all sets that do not contain.
Yes. I'll come to that. Yes. If you can just give me a minute, I'll do that. Okay. Now you take another set T. So T is a set which contains this 2, 3, 4, 87, 64, two different sets. And T is also a set, so you can put T inside itself. So it's a set which contains itself. It can be, I'm not rigorous when I define set. I'm just taking set to be a collection of some things. It can be anything. Okay, so I put T inside it. So T is an element of the set. So T contains itself as an element. Let's say if X is an element of S, we write it mathematically, we write X inside ES. Okay, so this is called X is an element of X. If it is not an element, we put a cross. It is not an element. Okay, for example, 2 is an N, right? 2 is a natural number, so it is inside N. 1.5 is not the decimal. For example, T is an element of T, it contains itself. Q is not an element of Q, right? Because Q doesn't contain itself. Okay, so Russell paradox is the following. So look at the statement that let R be a set of all sets that are not elements of themselves. So for example, in our previous example, R would not contain this set Q, for example. Sorry, R, it is just a set of all sets that are not elements of themselves. So R contains Q, right? Because Q does not contain itself, but R does not contain T, because T contains itself. So you take all such things, you take all the sets which do not contain themselves. Okay, so this seems like this is a statement. This is a perfectly fine statement to look at first time. And then if you look at this, if you want to write this mathematically, it is just the set of all x is a set such that x is not contained in itself. Okay, so this is what I write in mathematical terms. So the question is R contained in itself? R is a huge set which contains all the sets which do not contain themselves. And you take R now and you ask, is R contained in itself as an element? Okay, so again, there can be only two possibilities. R is either contained in itself or R is not an element of itself. Okay, so let's say, suppose if R is an element of itself, but R should contain only those that are not elements of themselves by definition. It is just all the sets which do not contain themselves. So R cannot be inside R. So R is not an element of itself. But if R is not an element of R, it contains all those that are not elements of themselves. So therefore R should be inside R. Right? So this is due to Russell. So he was analyzing statements like this, and he says, like, you know, if you put statements like this, if you define set to be any collection, then this statement doesn't make any sense. So R can be, so R is contained in R, R cannot be contained in R, and it's not the other way as well. R cannot be inside R cannot be outside R. So we don't know what it is. So it leads to paradox. So if you define R to be this, then the collection of the set of all, so R, if you take R to be the set of all sets which do not contain themselves, then R is inside the set if and only if R is not inside the set. Okay, so this is obvious contradiction. You cannot be in the set and you cannot be outside the set at the same time. Okay, so this is called Russell paradox. This is actually a variation of Barber paradox. If you look at it carefully, it is just the same thing, formulated in set theoretic terms. Okay, so now again another statement, a set of all sets. So a set of all sets is a monster set. It just contains all the sets that you can find. You take all the sets in the universe, put them together and form a huge set. It's the monster set or the universal set, the set of all sets. Then it looks perfectly fine construction. But then again, if you form such a set, then it contains all the sets that are not members of themselves because it is a smaller category. So therefore, it leads to Russell's paradox. Okay, because this big set should contain the sets which do not contain themselves, which is the Russell set. That is a contradictory thing. So it leads to self-contradiction. So S does not exist. Okay, so the set of all sets does not exist. Okay, so this is not a consistent statement. Okay, so there's nothing about right or wrong, but then the statement itself contradicts itself. Okay, the problem is that just that the definition of set is too naive here. So when I defined set before to be the collection of anything, you put anything, you collect anything and then you put them form a set, is not the right definition of a set. It is just too naive. So people looked at these, mathematicians looked at these paradoxes and then they said, like, this definition of set is too naive. So they had to refine, they had to put some more axioms to make set more, more consistent. Okay, so forming a set without any restriction and what it can contain, what it cannot contain leads to Russell's paradox. It leads to inconsistency. So therefore, they developed new theory called Zermelo-Fraenkel set theory, which avoids paradoxes like this. So they put new axioms on what it can contain, what a set can contain, what it cannot contain, and so on. Okay, so another paradox is called the liar paradox. So let's say I say the statement, I am lying. Okay, so I say this, I am lying. Now the question is, am I lying or not? Okay, so there are two possibilities. I'm actually lying. If I'm lying, then I am lying is a lie. If I am lying is a lie, I'm telling the truth, right? If I'm telling the truth, I'm not lying. So if I am lying, I'm not lying. And the other way around is if I'm not lying, that means I am lying is the truth. I am lying is true. If I am lying is true, then I'm actually lying. So I am lying only when I'm not lying. right? Okay, so this is again a paradox because I am lying is self-contradictory. So there is, I'm not lying, I'm not telling the truth, then what am I saying? Okay, so another thing derived from liar paradox is called the this another paradox which is derived from there. It is the statement that this statement is false. Okay, if you look at this statement carefully, it seems like fine, it's a perfectly valid statement. But if you ask this question, is this statement true? Again, there are two possibilities. The statement is actually false. If the statement is false, then the statement is false and the quotation is actually false. That means the statement is true. Again, if the statement is true, then the statement is false is actually true. That means the statement is false. So a statement is false. A statement like this is self-referential. It refers to itself and leads to contradictions. Okay, so it's a paradox. So now the statement is neither true nor false. Then what is it? Okay, so if a statement is neither false nor true, what is it? So forget about proving something. If you're not even sure about the statement, what about this? All this, story about mathematical proofs comes from proving some statement. If the statement itself is not consistent, forget about proofs. Okay, so you want to acknowledge that there are things like this which you should be careful about. Okay, there are paradoxes in mathematics. When you look at it first, it seems fine, but then if you look at it closely, there seems to be some logical contradiction in the statement itself. Okay, so this is a quote by Edward Kistner. The greatest paradox of all is that there are paradoxes in mathematics. Okay, because you think that mathematics is a very rigorous subject and then everything has to go by logical reasoning, but then there are also paradoxes, okay, in mathematics. They are not necessarily bad. They are not, it's not something that is negative. You may ask, like, what are paradoxes then? Well, are they just silly thought experiments? Are they useful at all to prove something? Okay, how you started with proofs, and then we saw about we saw paradoxes which go against human intuition, and now we ask, well, you have this paradox, that is the reality, that is the truth. There are paradoxes. Now what do we do with this? How does it help in mathematics? How do we know more from these paradoxes? Okay, so this was analyzed by Godel. So Kurt Godel, he's a very very influential philosopher and mathematician, and he actually looked at this statement, the liar paradox. He looked at more carefully, more deeper than we do, and then he thought about the limitations of mathematical proofs. Okay, so well, there are some self-contradictory statements in mathematics. Then he suspected that mathematical proofs does not exhaustively cover all the truth. There may be a lot of true sentences out there, and he was questioning whether mathematics can prove all the statements that are true. So he did some work on this, and briefly his work is the following. So what he did was he started with a set of axioms, like we do in mathematics. You start with a basic set of rules, axioms, like you have axioms for natural numbers. You start with this, and then you build some theory on it. So he started with some set of axioms, and he translated mathematical statements and equations into numbers. So each equation had a number associated to it. Each formula had a number. So every formula, complex and non-complex, each had a number. He associated a unique number to that formula. And that number is called the Godel number, named later. And this coding allowed mathematics to talk about itself, the set of axioms from which this is built. He could talk about this, the whole set of arrangement of starting with axioms and formula. He allowed this coding to talk about itself in some way. Okay, so this is very vague, but then the idea is that once the system talked about itself, it arrived at contradictions. Using this, he was able to write something like, this statement cannot be proved as an equation. Okay, something of that sort. He wrote it in the form of a mathematical equation, and this created a first self-referential mathematical statement. This statement cannot be proved as a statement, using a formula in a given set of axioms, produce a self-referential mathematical statement, and that means he proved that something cannot be proved. Okay, so you start with an axiomatic system, and then you look at all the things can be proved, and it looks like there are some things which are true, but which cannot be proved using the set of axioms, no matter what you do. You can increase the set of axioms, but still you'll not be able to prove something in it. Okay, so this led to what are known as the famous incompleteness theorems or completeness theorems. I don't know which way people call the Godel's theorems, which is the first theorem is that unprovable true statements exist in every axiomatic system. There will always be true statements that we cannot prove. It doesn't matter what axioms you start with. You look at all the truth in the system, all the possible statements that are true, and you look at all the statements that you can prove to be true. Those are different sets. So the first one is a bigger set. There are always some truth out there which you cannot prove. Sorry? Oh, I didn't hear it. Sorry. Okay.
He said why she confessed.
Oh. Okay, the second theorem is that the system cannot prove its own consistency. So even if you build a system like this with axioms and you look at all the statements, there is no way to show that your system that you built on is actually consistent. There's no way to show that it will not contradict itself. It will not lead to paradox. It is not possible to show these things. There is actually a theorem. There is a funny thing. There's a theorem. He proved the theorem that you cannot prove everything. There's something that you cannot prove. There are always some things which you cannot prove. And you cannot tell whether your system is consistent. You cannot tell whether there's going to be contradictions or not. Okay, yes. Sorry, I can't hear you. Yeah. Yeah. It's an unprovable statement which does not have a proof. But there are true statements. There are something which is true. You know it is true. There are true statements, but there is no way you can mathematically deduce it. Is what he's saying. There are true statements, but there is no. There is no examples that I can write down, unfortunately. No, but there is a proof. There is a proof for that. There is a proof. There is having no counterexample does not establish the statements to be whether it was true or not. But what he's saying is absolute. He's saying that no matter how smart you are, how smart mathematicians are, there are always some statements which cannot be proved. There are true statements which cannot be proved in any axiom. You can increase your set of axioms and build a new system. Even in that new system, there will be some new statements, some true statements which you cannot prove. What?
Will this be true in the other direction as well? Like you make your axioms really simple and basically your system has no power to prove anything. But
yes,
will it still contain statements?
Yes, anything that you start with axioms, any set of axioms. They can be extremely simple, as complicated as you want. All he's saying is that it is always. It's due to Godel. So. Okay, so the point is you have to embrace the unknown in the pursuit of mathematical truth. It's going to be. You start with axioms. If you don't have any rules, you cannot play the game. Sorry? Every axiom. Yeah, because you can keep changing our axioms. Like first, for example, I gave an example of set theory, set axiom. Naive set theory means set is just collection of any set of objects. It didn't work because it had some problems, paradoxes. So they refined something more. You put some more axioms. But then the thing is, it doesn't matter what kind of axioms you put in the system. He showed that there will always be something like this, no matter what your set of axioms is. Okay, so there's just there are unknown things which are true, which you will never be able to find. You will never be able to prove. I think that's it. Thank you.
We'll just take some online questions and then we'll break for the tea and come back, and then of course you can ask the questions again. So the question is the visual proofs when you discussed earlier.
Yeah.
Are they always exhaustive? Yes.
Exhaustive.
In the sense like they say that visual proofs are basically, the question is visual proofs are just drawing and geometric objects can't be perfectly drawn by humans. So how can we take them as exhaustive?
Oh, as exhaustive. Why is it a valid proof? Why do you consider? See, the thing is, the drawing that humans make may not. If I draw a circle, it may not be a perfect circle. It may not be a straight line. But the thing is, you know that you can draw a circle. You know that you can draw a line. I think this again comes from an axiom. An axiom. There is axioms which says like any 2 points can be joined by a line. You have to agree with that axiom, right? Once you agree with that axiom, then you can draw like this. There is no problem with that. You can draw 2 points. You can take 2 points. You can draw a line between them, and the entire point is if you have a straight line which is the largest of the other two sum of other two sides, and if you draw a circle starting with these as radius, then the only way that this triangle can be completed, no matter what the angle is when they actually overlap on A. Right? The circles have to overlap in order to complete the triangle. That is actually comes from basic set of axioms from geometry. Right?
I guess the question is answered. So just 3 announcements before we break for the tea and close the online session. So the next time, right, that is on 18th of February, will be about powering the future. It's about new methods the scientists are trying for as a source of power. So it's about that. Rohit Mann will talk about it. Then on 23rd of this on the 18th at on 23rd of February, there is a public lecture at CIFR, and the title is about artificial intelligence, and I think it will be interesting. And the final thing is on 25th of February, that is the last Sunday of this month, CIFR will be celebrating the National Science Day, and you all are welcome to visit CIFR on that day. So you can visit lab, listen to the lecture, it will be a full day activity there. So with this, let's thank Srimati once more. So we'll break for the tea and come back as soon as possible because I think you have a lot of questions. I close the